Hello and welcome to the lecture LSTM. In this lecture, we are going to start with problems of recurrent neural network. We essentially understand vanishing gradient problem and long-term contextual dependency issue. Then we introduce LSTM. Then we'll try to understand the LSTM architecture, and finally we know how LSTM solves the vanishing gradient problem. So there is some problems in recurrent neural network, or we should say a simple recurrent neural network. The first problem what we have seen or just introduced is a vanishing gradient problem. So the backpropagation through time has been used to train RNN. Now in PPTT, the gradients are multiplied repeatedly across time steps. That we have seen in our last lecture. That how these gradients are multiplied repeatedly, kind of chain rule across the time steps from the final steps to the initial states. And if these values, that is gradient values, are less than 1, so these gradients shrinks or decay exponentially, and that is very, if we keep on multiplying a number with a less than 1 number, then definitely it shrinks very fast. So what happened? Whenever we approach to final layer to the initial time layer or initial time steps, the weight updation of RNN nodes become unstable. That means weight updation become very slow, because there is no gradient is there or is very close to 0. So weight updation is negligibly small. This because of due to very low or close to 0 error gradient, especially for long. So this is called the vanishing gradient problem. We'll see in bit mathematically that how actually it happens. And as a result of this vanishing gradient problem, RNN only focus are very local. That means very number of time steps, very few number of like 5, 6, maximum 10, not more than that. So RNN focuses on recent inputs, but it can't remember the distance information very well. That is because if the time steps is high, then it start forgetting because of this vanishing gradient problem. The initial time steps, the error gradient is exponentially less or decaying, very close to 0. So it cannot be converged or it cannot be learned properly. And this limits this particular problem, limits the performance of RNN on long sequences. If there is a long, this is a DNA sequence or a very long sentence to understand, then RNN is not going to perform very well. That is another big problem of RNN. Another thing, RNN, that was a bit inherent, that in RNN, since it handles the sequential data, then generally we see the one time step is depend on the previous time steps. Just for example, for a sentence, a later word depends on the, or syntactically or constructically on the previous words, like this. RNN node in each time step depends on the previous time steps node. So due to this sequential nature, all time steps cannot be performed or cannot be computed in parallel. Since there is a very less parallelization or less parallelism, the resulting the what result is very slow training because no parallel processing is there. And due to this less parallelism, the GPU utilization is not that much good. So these are the major problems that RNN basically going to face. Now, before to solve these problems, we like to understand this vanishing gradient problem from a bit mathematical point. Now here, what we understand from our previous discussion, this is the formulation. Here what we can see that in this particular diagram, there is the RNN4 RNN node we have considered, and what we have seen before that a particular this loss function, let's L4. This L4 is basically, if we consider this L4, now how these WHs are being trained, or we obtain the value of WH by repeated weight updation. Okay, so that equation what we have, think we remember just last lecture we have that was del of t of del of W of h. This is error gradient with this error and with respect to this WHs. And since these WHs is basically are connected with each other because this is depends on this depends on this and so on, so that we have come up with this del of L of t of del of t, sum it up over I is equal to 1 to t, where t is this O, and this del of ht, del of hi, del of hi, and del of wh. So that is our formation. Okay. Now the question is that this part, this del of ht of del of hi, this particular part, you can say this is a kind of chain rule, but it's in this format. Now this thing, now these two index, that will be very careful. Now if this I and t are too far apart, that means if this, let's say it is not 4, it is 400, and we find out this h1. Now you can understand so many layers or so many time instants in between. Okay, so what we have tried to imagine that this del of ht of del of hi, this I and t be if this is very far apart. Let's say for example it is t and it is I1 and this t is basically capital T is 50. So 50 or more than 50, 100, 200, 400, whatever. It's a very big number. If such situation happen, then what will be the problem? Okay, that let's try to understand. Now here, if we expand this W, this del of ht, del of hi, if we expand this, then what we get, del of ht, del of hi is equal to del of ht, del of ht minus ht, and this kind of chain rule kind of thing. So essentially if we write it here, so it is a capital pi, this means it is a that multiplication, m is equal to I plus 1 to t del of hm, del of hm minus. So this is going to be here we are going to find this. Okay, so this is the basic formulation. Now what is this is, if we see what is this, if del of hm, del of, what is the functionality hm and hm minus 1, that we know that our wh into hm minus 1 plus base plus wx and that input at this time instant. So here you can see that what is this, we actually try to understand what is the relation between h to h1. It is hm minus am or it hm minus 1. So what formulation is this? hm or h2 is basically that wh to h1 plus wx into x2 plus and then we some non-linearity tan h non-linearity, so we can get h2 exactly and some biased exactly right, and we put this same is right tan h of am. So hm essentially tan h of wh into hm minus 1 plus this bias plus w. Now this is basically for this particular h, this is constant kind of, so can be collected. So if we have del of hm, del of hm minus 1, then it is called del of hm, del of am, del of am h. In this way we can, and is our case it is the t, the number of RNN nodes is t, it may be a bigger term. So if we write this equation del of hm and del of am, this is basically a matrix and it looks like this: del of hm minus m1, del of am1, del of m2, del of so on. But it's very important to understand here, you just try to see the off diagonal element del of hm2. So if we are taking derivative, but it is not involved here, this am is not is there, so all the off diagonal element is actually becomes 0. So this is basically become a diagonal matrix of such form: del of hm minus 1, del of am1, and this is the first diagonal element. Next diagonal element del of hm2, am2, del t, and so this is this diagonal matrix. And what is this if we to put it here? If we take the, it's basically a tan inverse h, a tan h bar, that is tan h derivative of tan h of am1 and tan h of am2 and so on. So it is basically a diagonal matrix of this diagonal element of am, because 1 2. Okay. So with this mathematical formulation we find del of hm, del of hm minus 1 is equal to del of hm by del of am, del of am by del of hm minus 1. Now what we have find that this del of am by del of hm minus 1, this part, it is wh, from where it is coming. Now we know here that this is am equal to w of h and plus b of and plus wx x. Now if we take a derivative of this respect to h of m minus 1, what we are going to get? This is becomes wh, this is constant, this is constant, become 0, so it is become only wh. So this is exactly what we will get it: del of am, del of hm minus 1 wh. And what we get, our del of hm by del of am, where here it is, what we get, that this is basically a kind of matrix, a diagonal matrix of tan h of am. Now if we put it here all together, so this is diagonal of matrix of this with, and this is WH. Okay, for this reason. So ultimately what we get? We get del of HM of del of HM minus 1. Why actually we want to find out? Here you can see we are trying to find out this. Now if we have find out this, what does this mean? We get it, this del of HM minus 1, that is W, so just transport for this equation, and this diagonal matrix. Now this is important. If I go back to our this thing, what is our del of HT of del of HI? That we have expanded like this, and we get this. Now we get this here. You can see this term we get, and this is that on multiplication I plus 1 to t. Now here we put it here. Now so our del of HT, del of HI is basically this is the multiplication is equal to 1 to t of del of HM, del of HM. What does this mean? You can put it this WH transpose of tan H. So what is this? So this gradient, now it is very important. This gradient at the initial time instance. What is this? This gradient become product of many matrices, and that is major essential thing to understand. Where as per our assumption I and t are far apart. If I is equal to 1 and t is equal to 50, this t is equal to 50, so you can understand this. Okay, so this is the major understanding. Now if this is the case, then I is equal to 1 to t, where I is equal to t and t, this kind of thing is that. Don't confuse, this is for transpose, and is equal to this, you can say. Then the gradient becomes product of many matrices. And if this diagonal matrix eigenvalues is less than 1, and it can clearly understand why values is 1, the gradient is exponential. There is two reasons. One of these matrix eigenvalues is less than 1, and if eigenvalues is greater than 1, it gradient explodes. That is another. But it's this diagonal value is what is in general the case. We get a very less gradient at the initial layer. Another thing, this tan H is also less than, because this is tan H in derivative, so it is a differentiation of tan H. This is also less than 1, that you know. So in each multiplication often scales gradients by smoothing less than 1. So what we can understand, if this is a 0.9, so if we go to the power 50, it's very close to 0, almost 0. So what happened, even we start with a strong error gradient, if the number of time instance is large, or a sequence is large, or a sentence is big, then the initial part of the sentence or initial nodes of the sequence or elements of the sequence very problematic for RNN to model, because the gradient almost decay to 0. The error gradient decay to 0, and that essentially called the vanishing gradient problem with a simple RNN. We will see later in this course that how this vanishing gradient problem is handled. Now we are going to understand the problem of naive RNN or simple RNN by taking a example. Now, in our previous discussion, what we have seen that this naive RNN has this kind of architecture, a very simple architecture. This HT is basically WH, this WH is basically weight parameters, what is previous state input, and this WX is the at this t time instant input. So WX into XT plus WH into HT minus 1, and we put a tan H nonlinearity over this, and we again get HT. Now this HT, if we multiply it with WG and we put the softmax over it, we get the IT. So this is a very simple RNN structure. So what is important now, that given this very simple structure, what is the problem of vanishing gradient? And this vanishing gradient problem, how the cause the long range dependency issue. Let's try to see. Now here we take a very hypothetical example. At a sentence, the kid watching cartoon channel in the TV is very happy, and the kids cartoon TV are very happy. So just see that this is the plural and this is R, this is singular, this is this. What the important is, these two words, although it is placed a distance in a longer sentence, but it is somewhat related. This is depends on the what is the, it is singular or plural. If it is a plural, that is R. Singular, it is. Now, in this kind of example, RNN may not be a very good performer due to this vanishing gradient. So what we have seen in our previous discussion, that during this backpropagation through time, this gradient is get multiplied repeatedly. As we see, it is, if it is here, so this thing somewhere here, this particular word, and this error gradient is basically backpropagated through time in backward direction to come in this second. Now if this value of k is high, as per this sentence, maybe it's another longer sequence, longer sentence, but for our understanding, if this k is very high, then definitely this particular, when the error gradient coming here from this, then it is almost decaying to the zero, as per our understanding, what we have seen in this last few slides. So it's the error gradient decay or shrink exponentially, and if it shrinks exponentially or become almost zero, then what happened? The earlier time step stop learning, because we know that the learning means the weight updation, and weight updated, weight are updated according to the error gradient and the learning rate, as we have seen. So since this bigger sentence or a very big sequence, and then since this is a gradients are keep on multiplied, there are gradients at every time instances from final layers or final later time instance to the initial time instance, then it is almost the gradients is becoming very close to 0, and that essentially stop learning. So, and this is basically the vanishing gradient problem. So, this vanishing gradient problem, or because of this vanishing gradient problem, RNN is not that much suitable for very long-term contextual dependence. Now you see, this is somewhere related or dependent by virtue of the context of the language. So this contextual relation or this contextual dependency cannot be well modeled by this naive RNN due to this vanishing gradient problem. So that is the major issue of simple RNN. And here we are going to understand how this problem being solved with LSTM. The LSTM as a full form of long short-term memory has been proposed in 1997. And LSTM is basically designed to specifically fix the weaknesses of naive RNN. Okay. So how LSTM fix this problem of RNN? So essentially, LSTM introduces a memory cell, and that is we are basically going to understand this part of the lecture. What this memory cell do? That holds information over extended periods, addressing the challenge of linear long-term dependencies. So this memory cell is a capability of hold the important information over extended periods of time, and that essentially solves the problem of learning long-term dependence. Okay, now this memory shell is being controlled by 3 gates. So when we discuss this LSTM architecture, we understand that how these 3 gates, namely input gate, forget gate and output gate, is going to control this memory cell, which essentially solves this long-term dependency issue. Now see what this memory cell is basically going to do. To understand that this gate, what these gates are doing, we have this figure. Actually, this is a 1 unit or 1 node of this LSTM that has been replaced this very naive architecture of. So now this 1 node has been replaced with this. Now as we see here, there is a 3 gates, and these 3 gates basically control this memory cell. First is called input gate, this much. This gate, it controls what information is added to the memory cell. Okay, so this is information at the time instant t being added. So it is coming, that doesn't mean it is added to the cell. It depends on this input gate. So input gate controls what information is added to the memory cell. Next comes the forget gate. This is the forget gate. What it determines that the information is removed from the memory cell. So it determines what information is to remove from the memory cell. It essentially takes the decision, the information coming from the previous state, that is Ct minus 1. what portion of this information is being retained and what part of this information is being removed. Okay, that is by forget get. Now the final is the output get. That controls what information is output from the memories. So this is the output get, and it basically control the information which is as HTML. So what we have learned here, that there is a 3 gate: input get, forget get and output get, that is going to control this memory cell of LSTM architecture, and this memory cell is going to handle this long range dependency issue. Let to elaborate this. First we try with forget get. It controls memory. So what does this mean? In LSTM, the forget get controls how much of the previous cell state should be kept. That's what we have said. This is the information coming from the previous cell state, CT minus. So this forget get allows network to intentionally forget the irrelevant information. Now here the formulation of this forget get, FT. What is? There is a weight parameter associated with this HT minus 1. It is the state input from the previous state, and this WH and F for forget get, and HT plus WX of F. This is X. It is a weight parameter associated with input X T at this T time instant, and F for this forget, and B of F. F means for forget get. So this summation we put a sigmoid and nonlinearity over it. So now for a particular cell state, if Ft is equal to 0 or near 0, very close to 0, that memory, that CT minus 1 memory from the previous state, this is erased or is forgotten. On the other hand, if Ft is equal to 1, then this CT minus 1, or when Ft is 1 or near to 1, the memory T minus 1 from the previous state passes unstained further. So you can say the CT is basically T minus 1 if it is 1. So this is the forget get. Okay. Now we are going for the input get. That is called selective writing. As we discussed earlier, in LSTM, the input get controls what and how much new information should be stored into the cell state. So in each time's instance, a new information by virtue of this xt is coming, and definitely ht minus 1 is also coming from the previous state. Now the question is, while how much of this information should be stored into the cell state, that is going to be determined by the input get. So what we have said, for what we have seen, forget get decide what to remove, where input get decide what to add. Now what is the formulation of input get? It is WH of I is for input get, this WH for coming this previous state HT minus 1 plus WXI for input XT at this time instant, I for input get, plus P of I input gate. This summation we put over this summation, we put a segmental nonlinearity and we get that. And what is the cell state? Cell state is basically this. It is the WHC. This is what C state of H of t minus 1. So this only the weight matrix are different. And same the weight matrix of input and this bias term. And we put a tan H nonlinearity over it. What? CT tilde. This IT decide what component is to be updated. And this CT tilde provides the change content. As we can see here, it is coming from okay. So cell state is changed in this equation. This is very important equation. This is f of t, this is for get. This is c of t minus 1 plus f t to c tilde t. Here this it into c t tilde represent the new candidate values scaled by how much to update its state value. Okay, because of this. And this ft into c t minus 1, this part decide how to remember the or what to remember from the previous state. Okay, so very simplistically we can think that this LSTM, whatever we have to get, we have discussed, that something we can taking from the previous thing and something it is from the input. Maybe some cases, the extreme two cases, the CT minus 1 is completely removed or completely passed as a CT when ft is equal to 0 and 1 in these cases. And sometimes this xt is also what kind of function is driven by this input gate. Okay. Now come to the final one, the output gate, the controlled exposure. What is the we are going to output? So the output gate controls what part of the cell state is exposed as the hidden state. The actual output of the LSTM at the time step, that particular time step. So hidden state is basically usual input. This. So the cell state CT stores long-term memory, but it is not always required to expose the entire memory at every step. Okay. The output gate controls how much of the internal memory should be exposed to the outside world at this time. That is very important to understand. That this output gate is essentially control HT, and this HT is going to be outputted. CT may not be outputted every time. What is the cell state? CT stores long-term memory. But it is not always required to expose the entire memory at every step. It is very important and interesting concept. So what essentially this output gate is, that is very similar to the other two gate, WHO, this O for output, HT one, XO for XT plus BO output, we put it on. Yes. A sigmoidal nonlinearity over this. So this is the output gate. Okay, so this is the major understanding of output gate. Okay. Now that this output gate, the current cell CT is passed through a tan H activation. You can see CT is coming from a tan H activation to scale its value between plus and minus 1. Finally, this transformed cell after this timing is multiplied element wise with OT. That OT means this our output gate to produce the hidden state entity. So that is this dot in the circle is called element wise multiplication. So this HT is thus produced. So that is very important here. The cell state stores long-term memory, but it is not always required to expose the entire memory at every step. So that's why which part is going to be exposed at that very time step is defined by this concept, by this. Now, how LSTM solves the vanishing? We have this formulation and this kind of structure. This is the t minus 1 state. This is tth state. It is t plus 1 state. And this there is. So this cell state is very important. Now we can see the LSTM introduce a memory cell that is called cell state, and getting mechanism that by this virtual this forget gate, input gate and output gate that regulate the information flow by virtue of this equation that we have discussed. CT is what part of the previous thing is forget, or we have bypass what part, and which part of the information is going to be added by this input gate. The core idea is this: the cell state CT is changed slowly. Now this you can see here, this is a kind of flow with only minor linear interaction. You can see this is a very minor linear interaction is there. It is very easy to information to flow along it unchanged. Now this is the reason that vanishing gradient is not going to problem. Okay, that instead of repeatedly multiplying hidden state as what we've done in Fermi, LSTM has a cell state which additive updates like this. You can see this is just additive byte, and this is just a gate also. So information is added, not repeatedly multiplied. This allows the gradients to flow backward without shrinking rapidly. You just see here, if we go in this is in forward direction, if we go in backward direction, in this particular, this is very multiplication, mostly addition of information. What part to remember, what part to forget, that's all. So it's a linear interaction. So this allows the gradient to flow backward without shrinking rapidly because of this linear interaction. This is called constant error curves. Let's see. So gradient can travel across many time steps with this pipeline and without vanishing, and this essentially solves the vanishing gradient problem. That is the one, the major understanding of LSTM, where LSTM is very, very useful because of we have to understand this cell state concept. It is not multiplied many times, rather it added. So the gradient flow backward without shrinking. So this is the main reason that it handles the one you can see not exactly but very similar of the skip connection what we have discussed in case of ResNet. Some analogy, somewhat similar. Okay. So this is the way ResStem solves the fallacy. Now we are going to see that how LSTM solves this long-term dependence. Now take example. This sentence, the book which I read last year and absolutely loved was fantastic. Now in this sentence, the verb was depends on book, not loved. If you going to implement or model this sentence, well, hypothetically we can say it's a long sentence. A simple RNN may forget book because this word and this word is far apart. A distance in a sentence is relatively high. So now the question is how LSTM fix this. So as we have seen before that LSTM introduce a memory cell that is called cell state and gates that control this information. And that is the main innovation of the cell state highway that we have seen here, this highway. That which allows gradients to flow almost unchanged over many time steps. And that is the main reason or main advantage of LSTM over the neighbor. Okay. Now what it is being said that instead of repeatedly multiplying it, that is the case in the when the neighbor and in this BPTTL. LSTM has a cell state with additive updates like this. It's called FT, CT minus 1 plus IT tilde. So if forget gate is 1, then CT is almost close to the FT. So this information is just flow here without changing anything. So that means information or the gradients pass through almost unchanged, which preserve long-term dependency. So it is coming unchanged when backpropagated is also. Now see here, it is hypothetical. If FT in between is 1, so here this book, the information of this is being carried up to this. So FT is equal to 1, CT is almost similar to CT minus 1. If maintain all these states, then we can get this. At least by this, we can the long-term dependence. Okay. So in this lecture, what we have discussed, we understand that what is the problems of RNN, vanishing gradient, long-term contextual dependency. Then we introduce LSTM, learn this LSTM architecture and how LSTM solve vanishing gradient problem and this long-term contextual dependency issue. next lecture we start the part 2 of this.